I need another, I think.
Okay, before to starting, I ask to all the participants to turn off your microphone to not disturb the speakers and turn on only when you want to speak. Thank you.
Okay.
Okay.
So we can start. We can start, right?
Yes, thank you.
Thank you, Lucia, for your head. So we are here to the third session of Computational and Applied Statistics, and we have two presenters in this session, and the presenters know the rules. I think you have 8 minutes for your presentation and more 2 minutes to ask questions. If additional questions some participants can put on the synchronous platform Riot available. So we start with the first shadow presentation that was presented by Sarah. Sarah, you are here, and the title of this presentation is Environment Performance Assessment of the Transport Sector in European Union. If you are ready, you can start, Sarah.
Okay.
You can share, you know.
Mm-hmm. Are you seeing the presentation?
Yes. Yes, everything is okay.
Okay. Good afternoon. My name is Sarah, and I'll be presenting the paper Environmental Performance Assessment of the Transport Sector in the European Union. This presentation is divided into 5 sections: the motivation, followed by the objectives, the methodology, where I present the benefit of the doubt models and the sub-indicators selected, the performance assessment, and the conclusions of this work. Transportation is a very important sector in the European economy. Between 2010 and 2050, passenger transport activity is expected to grow by 42% and freight transport activity by 60%. Following this growth, the greenhouse gas emissions from this sector have reached 22% of the total European GHG emissions in 2015. In 2011, the European Commission published the White Paper on Transport that proposed deep changes in the sector with the objective of making it more sustainable and efficient. Some of the goals mentioned in the paper are the 60% reduction in CO2 emissions by 2050 in respect to 1990 levels, the phase-out of conventional fuel cars from cities by the same year, and the improvement of road safety. In this scenario, it is important to be able to measure the sustainability of transport policies concerning the European Union countries. Therefore, the objectives of this work is to evaluate the environmental performance of the transport sector in the 28 European Union countries from 2015 until 2017 towards a more sustainable mobility. To achieve this, it was necessary to identify and select relevant transport indicators, to aggregate these indicators into composite indicators using the benefit of the doubt models, and finally to evaluate the environmental performance of the transport sector of these countries using their CI results. The composite indicator used is derived from the DA model proposed by Church, the benefit of the doubt model. This model is equivalent to the DA input-oriented model with only outputs, what we call the indicators, and a single dummy input equal to 1 for all countries. The advantage of using the DA model is that it does not require prior knowledge of weight factors, and it is unit invariant, and this facilitates the aggregation of indicators with different measurement units. The first model used to obtain the composite indicator was the original benefit of the doubt model that maximizes the weights of the weighted sum of the indicators. This formulation is subjected to 2 kinds of restrictions. The composite indicator cannot be greater than 1, and the weights cannot be negative. This allows the weights to be freely estimated, and in some cases, the model can assign 0 weights to some indicators. This is a situation that needs to be avoided, as with a 0 weight, the indicator would have no influence in the final index. To solve this problem, in the second model, we add an additional restriction that requires the virtual proportional weight of the indicator to be greater than a value alpha. Another issue is the presence of undesirable sub-indicators, that is, indicators where the increase of their value is not beneficial. For example, the GHG emissions. To solve this problem, there are some transformation techniques, such as the inversion of the sub-indicator, the subtraction of the indicator from a sufficient large number, or the use of the maximum minimum methods. The indicators selected to compose the CI are the share of buses and trains in the total passenger transport, that shows the share of collective transport in the total, composed by buses, trains, and passenger cars. The people death on road accidents, that measures the number of fatalities per 100,000 inhabitants and reflects the European Union goal of reducing fatalities close to zero by 2050. The share of energy from renewable sources in transport, that shows by how much renewable energies are replacing fossil fuels. The GHG emissions by fuel combustion in transport, that was collected in 1,000 tons and normalized using the country's population and to take into consideration the scale of the country, and it shows the transport contribution in the country's emissions. And the average CO2 emissions per kilometer from new passenger cars, that reflects the improvement on vehicle propulsion and energy efficiency performance. This table shows the mean and the dispersion coefficient of the sub-indicators selected. The highest variability relative to the mean was observed in the renewable energy share and the GHG emissions indicator, reflecting the different availability of renewable energy and the emission policies differences in these countries. The lowest variability was observed for the new cars emission indicator. The graphic on the right shows the sub-indicator means for each year in relation to 2015 levels. This way we can see that overall, deaths on road accidents had the greatest decrease and the share of renewable energies the highest increase in these years. This table shows the mean and the standard deviation of the coefficients obtained for each year using both models. Overall, using the first model, the average of the transport environmental performance has increased by 2.8% between 2015 and 2017. Using the first model, 8 units were efficient: Denmark, Greece, Malta, and the Netherlands in 2015, Hungary and Romania in 15 and 16, and Sweden in 2017. When using the second model with the additional restriction, only 4 units remained efficient: Hungary in 2015 and 16, Romania in 2015, and Sweden in 2017. Under the second model, Spain, Greece, and Belgium had the highest improvement, increasing in 2017 by 79%, 70%, and 13% above 2015 levels, respectively. Estonia was the worst performing country, with an average CI of 24 and almost no improvement during those 3 years. The countries were then divided into 2 groups: the benchmarks, which were the best performing countries that obtained a CI score above 95, and the inefficient countries that had a score below 95. The average values for each indicator for both groups were calculated and plotted in this graphic. This way we can see that the inefficient countries have less than 50% of the renewable energy observed in the benchmarks and more than 60% higher GHG emissions. In conclusion, the EU countries have slightly improved their overall transport environmental performance by 2.8% during the 2015-2017 timeframe, and the policies should focus more on reducing the GHG emissions from fuel combustion engines, in increasing the share of energy from renewable sources in transport, and improving the quality and access of public transport to increase their share in the total passenger transport. In future works, different models for treating undesirable indicators can be tested, and other sub-indicators should be considered to compose the CI. Thank you for your attention.
So, Sarah, you have 7 minutes. You have record time in your presentation. So we have time for questions. If some people want to make some question, please raise your hand in the left corner. Some questions? No questions. I have only one curiosity. You have 2 models to access, and in your conclusions you said as the future works you want or you intend to use other models. Have you any idea of these kind of models with restrictions, or we have already
Yeah,
solved?
another model that we are going to use for the undesirable indicators is to consider them as input instead of outputs in the
Okay.
composite indicator. Yeah.
Mm-hmm. You are, it's your dissertation in degree of PhD?
And masters.
Master's?
Yes.
Congratulations. You have a nice work.
Thank you.
Many questions? No one question. I want to thanks. This is my claims.
Thank you.
In my home. So if the next presenter is ready, Lino.
Okay. Yes, thank you.
You are ready to present?
Yes, I'm ready. If you want, I can start. I will share the presentation. Just a moment.
So I want to present you. I knew you, but some people want to know where you're from. The next work is multivariate analysis to assist decision making in many objective engineering optimization problems, and it was present. The presenter is Lino Costa, professor from University of Minho. So you can start. You can share. Right.
Okay.
You can start.
Can you hear me? Okay. Thank you for your introduction. As I am from the University of Minho in Portugal, and this is a joint work with Francisco Santos. In this work, we have applied a multivariate analysis to assist the decision-making process in many objective engineering optimization problems. First, I would like to show you the outline of my presentation. I will start making a short introduction. I will talk about the many objective optimization problems and the difficulties with the decision-making process in the presence of a large number of objectives. Then I will show you, or I will present you the multivariate techniques we have used in the context of multi-objective optimization. We have used the principal component analysis, cluster analysis, and also we have used some multivariate graphical representations to show the results of optimization. I will present some results applied to many objective optimization problems in the engineering area. The first one is a laminate plate design optimization problem, and second one is related with optimization of the radar performance. So finally, I will present, or I will address some conclusions and future work. I will start by presenting the formulation of a multi-objective optimization problem. A multi-objective optimization problem, the goal is to minimize a set of objectives. When this set of objectives is large, when we have the number of objectives superior to 3, we are in the presence of a many objective optimization problem. These problems are difficult because we are leading with a decision space. That dimension of decision space is the number of decision variables, and also a multidimensional objective space. When the number of objectives is large, this objective space is difficult or it is difficult to represent the trade-offs between the solutions. All solutions in a multi-objective optimization problem are compared in terms of dominance. I have here the definition of dominance, but we are interested in the optimal solutions. We have a set of optimal solutions, and the images of these optimal solutions constitute or form a front in the objective space. We have difficulties that are related with the dimension of the objective space. Just an example, I have here, I'm presenting here a plot, in this case a biplot, but this biplot is for a problem, the rather waveform optimization problem with 9 objectives. As you can see, the number of trade-offs, the number of solutions is very large. So the decision process is very difficult to perform, because you have to identify solutions that are that are related with different objectives, and the decision maker wants to identify the trade-offs and also wants to identify some similarities between solutions. In this case, when the number of objectives is very large and the number of solutions is very large, it is almost impossible to identify these trade-offs. So we have another problem that is related with the optimization process, because we also have difficulties when we are performing the optimization, because we have to compare the solutions. The comparison of a large number of solutions is very difficult. So, in general, it is clear, or it is interesting to use multivariate statistical methods to assist the decision-making process, what we call the offline decision-making after the optimization process. But also we can use these methods to help the search for the Pareto optimal solutions. In terms of using these some multivariate analysis in terms of optimization, principal component analysis is very interesting for the reduction of the dimension of the objectives. We can identify some redundant objectives and then exclude from the analysis these objectives. But we can also use cluster analysis for identification of similarities between solutions in the objective space and also on decision space. Graphical representations, these bar diagrams, scatter diagrams, and value paths are very common in the multi-objective optimization area. They can provide some information about the trade-offs, but we have difficulties for the large number of solutions. Even value paths are not so useful when the number of solutions is large. So biplots, for instance, biplots are a representation tool that can help the visualization of objectives and solutions, and can help to identify trade-offs. We can also use some other graphs like spider graphs, angiographs to complement, to assist or to provide more information to the decision maker. I have here two examples of application. The first one is the optimization of a laminate plate. This laminate plate is constituted by different layers, by several layers made of different materials and with different thickness. So the problem is to simultaneously minimize the compliance, the thickness, the total mass and total price of this laminate plate. So this is a mixed integer optimization problem with 4 objectives. And when we solved this problem, we have obtained more than 300 non-dominated solutions. I have here the bidimensional projections of the Pareto optimal front. You can see that we have some relations between the objectives. For instance, we can see that in terms of compliance, the objectives price, mass, and sequence are negatively correlated, but you can see, for instance, that mass and sequence are positively correlated with price. So we can identify some associations here, but in terms of the decision process, it's very difficult to analyze the trade-offs. So,
you have spent 9 minutes.
Okay, I will try to terminate. In terms of the application of principal component analysis, we can plot. We can see that the two principal components explain about 89% of the variability, and you can see using a biplot that we have in the two principal components, we have associations between price, mass, and sequence, and compliance is almost in the opposite direction. So if we use principal component analysis to reduce the number of objectives, and then we apply a cluster analysis to identify clusters of solutions, we have considered 3 clusters. We can see that these solutions are different, and we can choose representative solutions from each cluster. For instance, the solution that is closer to the centroid of the cluster, and we can also use other representations, for instance, the Anders plot or the spider plot to show the similarities between solutions. In terms of the b-objective projections of the Pareto front, you can see that the cluster analysis provides some additional information. I will not explain more. Just the other problem. For the radar performance optimization, we have a larger number of solutions, more than 11,000, and you can see in this graph, this is a path value graph, that is almost impossible to identify the trade-offs. So using or computing the correlations, we can find some information here. For instance, the objective F6 is not correlated with the others. Okay, and we can also use the others. Use the principal component analysis and the cluster analysis to inspect the information in this data. The same can be seen here. Okay. Just to conclude, this proposal is based on these methods. They are very useful to inspect association between the objectives and the identification of redundant objectives, and also the similarities in decision space, the similarity between solutions. These graphical representations are very useful to identify trade-offs. And as future work, we intend to develop strategies and to provide interaction with decision makers in order to select, for instance, the clusters that are most promising and so on, and also to include information that can lead the solutions to a given region of preferences or importance. So thank you for your attention, and sorry for the delay.
Don't worry. Thank you for your presentation. You have many objectives to present, and so I forgive you the delay in minutes. Somebody have questions? I have time for one question before close this session. Someone? Somebody want to make some question, some observation? So I only one comment, if it is allowed to me. You use the multivariate techniques to reduce the objectives in the problem or the number of variables. What is the purpose of the multivariate techniques?
Okay.
The PCR.
Yes. Okay. Thank you. Yes. In terms of the reduction of objectives. In terms of the use of principal components analysis, we intend to reduce the number of objectives, not the number of decision variables. That we are not interested in the reduction of the variables. But in terms of objectives, we can use principal component analysis with two purposes. The first one is of course to reduce the number of objectives, but second one is to provide information, for instance, for the optimization process in order to guide the search towards the optimal solutions. We can use this technique in these two ways. In terms of, for instance, using clustering, we can use clustering in decision variables for decision values to identify the similarities, but we can also use clustering in the objective space, and it is useful in both spaces. Okay, so I don't know if you.
Thank you. Thank you. I'm clarifying my doubts. Someone more questions? If we have no more questions, anyone? We have only two presenters in this session. We have time for questions. Additional comments, additional questions, you can use the Riot platform too, right? To contact the authors, to see the presentations, and to establish some connections. So,
okay.
I hope I rest to thanks to all presenters in the sessions, and I want to thank one more time to all presenters in all sessions of computation and applied statistics in this day. And I want to invite you to enjoy this conference. I hope you are enjoying at this time. Before CAST 3 session, we just attended a brilliant lecture by Professor Jenner, and the whole program designed by the organization promised to have a great moments. Have a nice conference program. By my way, I finish here. Thank you for your presence. See you next year somewhere in the ICCSA conference, I hope. Lucia?
Thanks to everybody.
Let's finish our session. Thank you for your support.
Oh, for nothing. You are welcome.
See you.
Thank you.
conference. Who is you?
Hello, I have restarted the live streaming of this room.
Ok, è uscito.
Ehi, volevo dire, ho riavviato lo streaming, ok?
Sì, però lui, cioè poi è stato interrotto nuovamente.
Sì, ma hai cliccato tu stop streaming?
No.
Ok. Allora, vediamo se adesso funziona. Adesso mi sembra che stia andando. Adesso qui non c'è nessuno che deve presentare?
No, siamo in pausa.
Ok.
Hi everyone.
Hey,
Hi.
I am Rastogue, and
Are you a speaker for the conference?
yes, in DASPA workshop.
Okay, in the next session.
Yes,
We'll start at 5:30.
yes.
Okay.
I want to make sure everything is okay before the conference starts. I will try to share my presentation, and we will see if you can see my presentation. Okay.
Okay, you can click on the button on the bottom left in the icon of share screen. Okay, perfect.
So you are seeing my...
Yes, perfect.
Okay.
Thank you. Okay, and see you later.
Thank you.
Lucia, una domanda. Quando si è stoppato, praticamente nessuno stava parlando da un po'?
No, praticamente siamo andati in pausa e è rimasto connesso un profilo che non so chi fosse e si è stoppata la diretta.
Sì, ma quanto è durato il tempo di pausa prima che si è stoppato il video?
No, pochissimo, era appena iniziata.
Ok.
Cioè io stavo caricando l'immagine per la pausa e si è stoppata la diretta.
Ok.
Quindi ora è ok, funziona sì, diretta. Ok, perfetto.
is on.
Lucia, per favore, puoi tenere acceso il microfono? Grazie.
Sì, eccomi.
Grazie.
Abbiamo finito presto.
Lucia,
Sì.
come vedi adesso sta funzionando. Io credo che si sia stoppato perché non rilevava audio. Cioè praticamente se c'è completa assenza di audio si lamenta.
Ah, ok.
Quindi niente, se per favore lo puoi tenere anche così, che sembra che...
Va bene, va bene.
Ok.
Perfetto. Grazie.
Lucia, non ti preoccupare,
Sì, sì, ho capito.
Stavo facendo una prova, ho messo sotto Paradisi in maniera tale che così con l'app
Sì, sì, sì.
inganniamo il demone che è sotto, capito?
Good afternoon.
È troppo alto il volume?
No, no, no.
Perfetto. L'importante è che non disturbi.
Okay, good afternoon.
Good afternoon.
Okay. Good afternoon to everybody.
Hi,
Hi. If you
I'm
want to
Raja
put,
Sheikh.
if you want to put your name, you can just click on the bottom right and insert your name. Thank you. I am the assistant of this session.
You, sorry, you are?
Yes, thank you. I am the assistant.
Okay, thank you. I'm the chair of the
Okay.
of this session. I'm Raja Sheikh.
Nice to meet you.
Nice to meet you too.
I will support in this session if you
Thank you.
need.
Thank you very much. Maybe I will need it.
For the chairman, I remember that you have to compile the evaluation form for each presentation. You know, yes?
Yeah, I received
Okay.
that.
Okay.
I received also an email from sent a video, and he told me maybe he will. So if it is possible that I can chair the participants.
Sorry, but I don't hear very well.
Yeah, I said that the first author sent me a video of his presentation, and he told me if he can't make it for the chair, if it is possible to share his video. I don't know if it is possible. Maybe I can test now.
Yes, I ask only 1 minute. Sorry, only 1 minute. Good afternoon for the new participant. If you want to put your name, you can do it by clicking on the bottom right and insert your name if you want.
Okay. Do you hear me? Hi, do you hear me?
Sorry, only 1 minute. I ask for the share, if it's possible to share this video, because I don't know if it's possible for the private and. But if you want to start and after.
Okay, but the first author is not here, so we can't start without showing the video.
And we can start with the second author.
Okay.
If you are agree.
Yeah, I agree with that. Is Moras there? The second author is Moras.
Yes. Hello.
Okay, good. So hello.
Hello.
So sorry, we will start with hello. We will start with your presentation, and after that we will see if we can show the first video. So you have 8 minutes and then 2 minutes of question. 8 minutes of presentation. Please go on.
Okay. So, hi everyone, I am Moras Fulbush-Togwe and I am here to present our paper named Anomaly Detection for Data Stream based on isolation forest using scikit multiflow. This paper is the first step of a project about scikit multiflow which concerns different universities. For this presentation, I will talk about different methods for an approach for anomaly detection in streaming context and discuss about the experimental evaluation we did to approve our implementation of eForest ASD method. Anomaly detection is a specific application of machine learning which identifies anomalies in the dataset in order to explain their presence. So detecting anomaly means to modelize the normal behavior in order to discover those observations which has not the normal common behavior. Detecting anomaly in streaming data is an important issue in a variety of real-world applications. It provides information like cybersecurity attacks. In the case of healthcare, it can help to discover or predict disease and to make some predictive action. In a specific case of context of data stream, methods have to be in single pass in unsupervised way, fast, and use low memory consumption. Talking about those framework which implement anomaly detection methods, Scikit-Multiflow is an open source machine learning package which is written in Python. It complements the well-known scikit-learn, whose primary focus is batch learning. In this framework, there exists a variety of streaming methods in many different domains, but in the case of a specific anomaly detection domain, there only exists one method, which is hash-based trees. So in this work, we want to contribute to add more anomaly detection method. The one I will present today is eForest ASD method. So the paper has two main contributions. First, we survey anomaly detection method in streaming. We classify them according to the approaches, and we highlight the advantage and drawback. In second part, we extended the framework isolation, the framework Scikit-Multiflow, by adding eForest ASD method. It was challenging because there don't exist any implementation of this method in the state of the art. In the state of the art, there exist many different methods of anomaly detection, but not all of them are adapted for data stream context. So we first distinguish those which are adapted for data stream, and we classify them in different approaches. The isolation-based approach is more adapted for streaming context because you don't need to perform any density or distance to detect anomalies. And this method, hash-based trees, is already implemented in Scikit-Multiflow. So we implement eForest ASD method in the framework. So how eForest isolation-based work? The isolation-based goal is to isolate data. The anomalies are very quickly isolated than normal data. And eForest is based on the forest of random and independent binary trees. Every node is split by choosing random attribute and random split value. The score of anomaly, the score of the data is computing using the average of the path length of the data in every tree in the forest. So now eForest ASD work. eForest ASD work with sliding windows, and in every windows, the method eForest is applied. And eForest ASD also deal with concept drift by using one parameter U. So when the anomaly rate is in the windows is upper than the parameter used, which is the anomaly rate, the concept drift is detected, and the anomaly detector model is updated with the current Windows data. Now, in order to validate our implementation, we did different experimentation, and we compare eForest, ASD, and hash-based trees. We use F1 score metric, running time, and the memory size because they are very important to the streaming context. We also use 3 different datasets which are well known in the anomaly detection area. Our implementation is open source and is available on GitHub. Hash-based trees is an isolation-based method, but it is different from eForest because it has fixed depth size and it cumulates mass on every node in every tree. Even his ways to split node is different. According to F1 score from our experimentation, eForest SD is more accurate than half-space trees. And like we can see here, eForest perform well with relatively small size, but half-space trees perform well with a relatively big size. Because eForest is depending on the data set which is imbalanced. So when the sample size is right, the abnormal data are not really representative, but half-space trees is not dependent to the data set. Talking about the running time and the memory size, because half-space trees has depth size, fixed depth size, and is independent to the data set, it has a constant amortized time complexity. So that is why half-space trees, like you can see here, is always faster than eForest ASD. Talking about the model size, eForest ASD use less memory than half-space trees. And like you can see, for half-space trees, memory size has no impact on model size. Only the number of trees increase the memory size. We can see it with the bar plot here. This is consistent with the update policy, which consists on updating statistic in the tree node with a fixed ensemble size. The choice of the appropriate method depends on the context constraint. So in the paper, we give some guidelines. Please refer to the paper for more information. To conclude, in this work, we presented a structured and comprehensive overview of anomaly detection algorithm for streaming data, and we classified them by anomaly-based approach. Every approach has strengths and weaknesses, and we highlight them. We also implement eForest isolation forest ASD in scikit multiflow. In the future, we plan to implement the adaptive Windows concept to improve concept of drift detection in both methods. We plan also to extend scikit multiflow with different existing methods for which we can propose some improvement for better performances. Those are some references we used in the paper. Thank you for your attention. If you have any question.
Thank you very much, Moraz. Thank you for respecting the slot time. Is there any question? We have time for since I'm the co-author of this paper, so I don't have a question for Moraz. So thank you, Moraz. So there is no question, we can move to the third paper. And the third paper is entitled Automatic Classification of Road Traffic Fiber-Based Sensors in Smart Cities Applications. And is there any author who is in the room, please?
Yes, I'm Salvatore D'Angelo.
Okay, hi. So please, you have 8 minutes of presentation and then 2 minutes of questions. Please go on.
Thank you. Okay, the work that I present with my colleague is automatic classification of road traffic with fiber-based sensor in smart cities application. In this paper, we have this work. We have used the fiber optic to as a sensor. So we have an introduction to fiber optic as a sensor and the distributed acoustic sensing. Then we have built an architecture for dust data and a pipeline for processing dust data. And we have some case study and the future work. The smart cities paradigm promises the provisioning of a vast basket of service for citizens, society, and enhanced by IT technology. So service like smart parking, air quality monitoring, noise monitoring, structural health of building. All these services require a capillary deployment of sensor to guarantee sufficient information gathering. All of these sensor networks have some problem. Is very costs. There is a problem of maintenance this sensors network, and there is some monitoring error. So we choose to use the fiber optic as a sensor. So this vibration, these sensors have a very modest acquisition cost. Statistically diagnose road deformation or problem. Is used also as a microphone, and so we can have detailed position and movement information, and there is no privacy issue. The sensor that we use is a DAS sensor, is a distributed acoustic sensor based on relay scattering. This sensor is a versatile tool for high resolution acoustic sensing and imaging. This sensor can be used for surface, seabed, and downhole measurements. And distributed optical fiber acoustic sensing are also used to achieve traffic detection, discrimination, and counting. This is where we are focusing. The architecture built for this data collection is the classic edge architecture, where we have three main functional blocks with the purpose of collect and elaborate the data, but also to reduce the cost to reduce the cost by balancing the computational capacity among the edge node and the cloud infrastructure. The sensing infrastructure is consisting in a number of fibers distributed along the road. In this case, the fiber infrastructure is already present because we use the telecommunication industry's infrastructure used for the internet connection. The interconnection network is the communication infrastructure that collects the data from sensing infrastructure and vehicles it towards the processing facilities. And the processing facility is implemented in the cloud to minimize cost and exploit advantages such as elasticity and centralized management and maintenance. Then we have the processing pipeline for DAS data. We have a sensing phase that is performed by fiber, focuses on measuring the signal in the space. The fiber section is posed on the street, and the events is detected by the fiber. In the denoising phase, numerical techniques are applied to enhance data readability and improve the effectiveness of classification. We use a discrete wavelet transform to compress, to reduce the complexity of the information. Then we have a preprocessing phase where the physical signal is measured and converted to be manipulated as a sequences. And then we have the classification phase. The aim is to discover groups of similar vehicles, analyzing the straight line extracted from each image by half transform. There is an initial training step which detects typologies from the pre-classified data. Then there is the online vehicle discovering step, in which incoming vehicles are allocated to one of the existing typologies or to new typologies if the new data behaviors emerge. The algorithm is also able to detect outliers. The proposed classification scheme is based on the closed stream algorithm. However, it has been adapted to work on features extracted by half transform. In the case study, we have a 4-section of fiber, about 300 meters of fiber. The 4 sections are parallel to each other and the light travels in both directions twice. In this way, the data has been detected 4 times in order to have a double validation of the detected vibration. 3 different measurements are at different frequency, 152 Hz, 19 Hz, and 9 Hz. The measurement units frame contain the measured value of 512 distributed microphone. The fiber is virtually divided in 512 sections, and if each section, each image contains 108 times. Every frames correspond to a time frame. At 152 Hz, we have a total of 832 milliseconds in each frame. At 19 Hz, the interval is about 7 seconds, and at 9 Hz, the interval in each image is 12 seconds. We have carried out from 5 to 9 passages with 2 different cars. The data has been processed in MATLAB by another team of the project, and then we have the raw data that is a big matrix with all the data. And then we have applied the denoising phase and the classification phase. For data analysis, we use some Python scripts with the help of the library NumPy, CPy, Pandas, and PyWavelet for the decomposition and reconstruction. Then we rearrange the matrix, and then we clean up the matrix of some distortion present at the end of the fiber. The step we perform for denoising are the following. Each of the 512 signal is decomposed with the wavelet transform up to the 5th level using the dB1 wavelet. The coefficients of the 5 levels are then selected, use a customized threshold for each level, and then the signal is reconstructed with the filtered levels. Once the signal has been cleaned up, we can proceed with the functional analysis and with the half transform for identification the test steps. The result of 3 passages is in this image. We have first passage at 10 kilometers per hour, 20 kilometers per hour, and 30 kilometers per hour. And the angle of the lines extracted with the half transform can be used for detect the speed. We are working on improving the measuring instrument to get a cleaner and better result. And we would like to take experiment with more vehicle configuration with different vehicles simultaneously and in opposite direction. Some of this testing is already done. And then we are working on improve the classification system to recognize more specific and articulate vehicles. And more experiments will be conducted on the road section using the existing fiber optic infrastructure provided by telco company. Thanks for the attention.
Thank you very much. Is there any question? No question. So I have one. Do you hear me?
Yes.
Okay. Would like to know if you did you carry out any comparison before choosing the right method for each step? For example, for classification, you mentioned that you use clustering. Did you carry out a comparison before choosing clustering as a classification method?
The method is chosen by us without any test, because we want to cluster in the project where we are working on we want to cluster the different vehicle in some category, and we want to identify this category.
And does it work well, the clustering? Maybe it is the good method to for your application, but what are the results from using it? Do you does it give a good result in your application? I'm talking about clustering.
But clustering,
does it work correctly?
Only some tests, and for now we have only a binary clustering where we have a vehicle or not vehicle, but
okay.
We are working on more tests and different vehicles to have more results.
Okay, thank you very much.
Thank you.
So now we can move to the last presentation of this session. Is there any author for the last paper, which is entitled a dynamic latent variable model for monitoring the Santa Maria del Fior dome behavior?
Yes.
Okay.
Can you hear?
So if I hear you. So if you're ready, you can go on.
Okay. So good afternoon. I will share my screen. Let me see if you. Can you see my screen?
Not yet.
No, because it's in addition to clustering one.
Can you see it?
No, not yet. But we are able to see you.
You can click on the icon on.
Okay, I'm clicking on share.
Yes, and after in the other window, there is share, I think, I suppose.
Okay.
Oh.
I think we lose him.
I think there is problem with the connection.
Mm.
Okay.
Okay.
He's back.
The Chrome crashed. So
Okay, now we are able to see your screen.
Okay, good. Okay. This is the outline of my talk. I will give an introduction about the Santa Maria del Fiore dome and its monitoring system. Then I will explain what are the aims of our study. And I will briefly go through the preliminary analysis to focus on how we model the dome's dynamics, and then I will report our major conclusions. So the Santa Maria del Fiore is the Cathedral of Florence. Its dome, it was built between 1296 and 1436, and it's, broadly speaking, its dome is made of 8 webs which build on an octagonal tambour. The first cracks in the dome were documented since the end of the 15th century, and since then they have been expanding, which is a problem because they may cause the overall structure to be unstable and eventually to collapse. So actually there are 2 main monitoring systems installed on the dome. The first one was set in 1955, while the second one was set in 1987, which is the one that we consider in this application. It's made of 166 electronic instruments, which comprehends deformometers, thermometers, piezometers, etc. And on total, we have 6 million measurements, which makes it one of the most accurate static control system ever put on an historical monument. However, what is the aim of our study? The dome's dynamics is unobserved, and we want to learn its dynamics based on the individual measurement sensor. And possibly, in doing that, we also want to achieve some form of dimensionality reduction. Of course, preliminarily, we have to go through some data cleaning process because we have some missing data and outliers. These are caused by storms, blackouts, earthquakes, which cause the sensors go out of calibration. We treat outliers as missing data, so we preliminarily remove them, and we retain in our analysis 57 out of the 66 deformometers, which are those that contains less than 10% of missings. The imputation procedure, I will be brief because it's well explained in a previous paper by Bruno Bertaccini. Basically, it constitutes of 2 methods. One is a quadratic sinusoidal regression model, and when this is not enough, a cascade procedure is adopted where the air thermometers, which have a complete time series, are used to input the time series of the imaginary thermometers, which are then used to impute the time series of the deformometers, which are the time series that we use for this application. So you can see the reconstructed patterns. The goodness of fit of this procedure is pretty good. Indeed, for most of the sensor, the goodness of fit measured by the R-square index is very high, like 90%, 87%. So it's pretty good. And with this at hand, how do we model the dome's dynamics? So we do this with 3 ingredients. The first is a vector of time series, which are the time series of the deformometers. And then we use, right now it's a bit abstract, but we use a generalized dynamic principal component, which is a vector with k legs. And then we define the reconstruction of the time series as an affine function of this principal component with a set of offset and loadings. The offset, which is the alpha j parameter, and the loadings, which are the beta j's, are specific for each time series. while F is common to everyone. So the idea is that we have a common underlying pattern beneath each time series, which is latent and we do not observe it. And the objective is to reconstruct find the best reconstruction of the actual time series using the first generalized dynamic principal component by minimizing the mean square error of the difference between the actual values and the one that we reconstruct. The procedure goes iteratively. Basically, and very broadly speaking, alpha and betas are estimated via OLS, and then the F is updated. And this procedure goes on until convergence. So here you can find the first 4 time series of the real-time series of the, let's say, actual time series of the first 4 deformometers. And here you can see the reconstruction. The reconstruction is pretty good. And actually the MSE is 0.066. So it's a very good reconstruction. In this panel, instead, you can see on the top left panel the principal component, which corresponds to the vector F that I was talking about before. And we like it because it's very smooth, it's sinusoidal. And the other panel shows the loadings, which are colored with respect to where they are installed on the dome. And so you see the loadings are very interesting. They have very peculiar pattern and specular between the 0, 2, and 4 loadings and the 1 and 3 loadings. So with this model, we were able to detect the latent dynamics of the dome. We are satisfied with this model because it is also consistent with some theory of architecture. That is, we revealed what is known in architecture, or to people that deal with that, as the breathing mechanism of the dome. That is, this pattern here of expansion and contraction. And also we had a great reconstruction of the original signals. The MSE is very low with just 1 component, which means that we are able to reduce the storage of each time series to just 1 time series, which is one that corresponds to this pattern here, and a matrix of loadings and offsets. So it's very interesting from this point of view. And it also showed good convergence properties because we made some attempts with dynamic factor analysis, which is a model which is trying to capture underlying unobserved dynamics, but it had very bad convergence property in the sense that we reached the maximum number of iterations without having reached convergence of the algorithm. However, this procedure took about 3 days of computation using the last year's measurement. So it's something that has to be improved because the time series is much longer. So we can say that these results are promising, but they need to be extended. And also, what we would like to explore is, because, you know, the dynamics of the GDPC is very interesting, but it's in some senses too simplistic because it doesn't give us any information about structural dependencies, such that how each sector of the dome, each web influence the other, and also doesn't give any information about hierarchies. Because actually the domes are 2. We have an inner dome and an outer dome. So we want to give a higher level of detail of what we discovered with this application, and possibly we are also looking for some way to reduce the execution times. Here are some preferences, and that's all for this application.
Thank you very much. Any question from the audience? Okay, so I have one question about your presentation. The detection of the latent dynamics is done on historical data, right?
Yes.
So do you think, isn't it more interesting to predict it? Maybe it's more interesting to predict where the dynamics for the future, in the future.
Yes, indeed we can predict it, but of course to have a good prediction, we would need to learn the parameters for for the model that parameters I'm talking about, the alpha and beta parameters, and to make good prediction, you
need a long historical.
Long history. You see that the underlying dynamics is very smooth. So in principle, that could be done, but with more data to learn these parameters, prediction will be much better. So yes, the main concern is to have computation in yes, and to very short times.
Okay,
at least to reduce those times.
Okay, thank you very much.
You're welcome.
Okay, thank you. So the assistant,
yeah.
So what do we do for the first presentation? I have the video. I can send it to you if you want to share it with all the participants, maybe.
I'm sorry, but due to the problem related to copyright, the organizer said me that it's not possible to share video when the authors are not present. I'm sorry.
Okay. Okay. So we have only 3 presentations during this session. And I thank all the participants, all the authors, speakers, and thank you for your assistance also.
Thank you so much.
Have a nice evening. Bye-bye.
Good afternoon. Good afternoon. Good afternoon to everybody. I'm Lucia, and I am assistant for this session that is machine learning for space and Earth observation data. Are you here for this session?
Hello, Lucia. My name is Rodrigo. I'm here for presenting a session, I guess, in half an hour.
Okay, please, if you want to put your name, you can do it by clicking on the bottom right and put your name. That is more simple to interact with all the participants if you want.
Okay, I will just change my computers here because the first one that I was using was not granting permissions to the microphone.
Okay, perfect. Good afternoon. Good afternoon. Good afternoon, Rafael Santos.
Good afternoon.
I am
Hi.
Lucia. I am assistant for this session.
Okay, Lucia, thank you very much. We are going to start in 8 minutes. Is that okay?
Yes, 8 minutes.
Okay.
You will remember that you have to compile the evaluation form for the presentation. Okay.
I'm doing that. I won't do that for my presentation because it's not fair, but I will do for the other two.
Okay, thank you.
Okay.
For the other participant, if you want to put your name, you can do it by clicking on the bottom right. Thank you. Thank you, Lorenzo. It's more simple to interact. Thank you. For the new participant, if you want to put your name, you can do it by clicking on the bottom right and insert your name. Thank you.
Okay, Lucia, I think we can start.
Yes, yes.
I see two other of the presenters are here, and I'm going to present a paper. So, well, folks, good afternoon in Brazilian time, good evening in Italian time. My name is Rafael Santos, and I will be the chair of this session. This session contains papers from the Machine Learning for Space and Earth Observation Data. That's a workshop that was proposed by some researchers at the Brazilian Institute for Space Research, INPE, because we do a lot of work with space, the data from space, remote sensing, and the amount of data is huge, so we are starting to use machine learning for that. The first paper, just a reminder, each presentation should be around 8 minutes with 2 minutes for questions. And I'm going to present the first paper because the author, Olga, wasn't able to join us. The first paper is called An Approach to Classify Burned Areas Using Few Previously Validated Samples. And let me share the screen. Folks, can you see the screen?
Not yet.
What about now?
Not yet.
That strange Jitsi is nothing.
Nothing.
Oh, boy. Let me see if I can open it.
I don't know. You have click on the bottom left, and after you have a window when you have to click on the principal window and share.
Yeah, I was trying to open the PowerPoint. That's the thing. It works perfectly from here, but
If you want, I can share your presentation and you can only talk.
can you do that for me? Because I'm trying to open it and I can see it, but whenever I try to share with you, it just go blank. If you can do that, it would be a great help.
Yes. Just 1 second.
Last attempt here. It's funny, I can see the window, but it's just blank. But if you can help me, that would be great.
I don't know. It's the mystery of the Jitsi.
And everything works when we're alone.
Okay. I think is
yes, I can see it.
Okay.
So, well, I'm Rafael Santos. I'm going to present this work on behalf of Olga Wittencourt, that was the main author. Next slide, please.
Ciao, ciao.
Ok, Francesco, tanto insomma.
And I'm going to try to do that in under 8 minutes. We have Brazil is a large country, and we have a lot of biomes. Even if this picture that I'm showing you, it's from active fires in California, we have this situation almost all year long. We have a lot of different forest fires in Caatinga and Cerrado and in the Amazon biome. The problem is that we need to monitor that. We need to see what's happening, which areas are burning right now, and we need to keep tabs on that, because that's a lot of policy that's done in Brazil because of these burned areas. The problem is that Brazil is large, and some of the areas are very hard to get by. We can't even go there and see that a fire is going on or not. And we had some increases due to several different aspects of politics and economics, so the people are burning more forest. So we use remote sensing data for that, because we have most of Brazil is monitored regularly from remote sensing. This example is from a Landsat 8 satellite. That's also a satellite we use. It's a 30-meter resolution, spatial resolution, and it passes over the same point every 16 days. Next slide, please. So how do we know? We are not monitoring. We try to monitor fire in real time, but sometimes we just need to know if a fire happened or not. So what we do is that we get images from the satellite in different timestamps, in different passes of the satellite. You can see on your left that we have 3 images from the Landsat, I guess. And what we do is that we check the difference from one image to the next one, or to the previous one. And on the right side, you can see 2 possibly burned areas. We call them possibly burned areas because for right now we know that they are different. The images are different, and that's the regions where they're different. But we don't know yet if they are burned, if they are caused by erosion, or they're caused by the deforestation. Next slide, please. So what we do is that we try to find all the polygons corresponding to changes on the images. And we have some basic algorithms that can say, oh no, that was a forest burn, and we got this scar on the image. Or we don't know. Sometimes we just say, oh, the image is changed. In the middle one, you can see in the middle row, it's not a forest burn. It's a part of a field that was replanted for some reason. So it's different from the image. It's different from the previous image, but it's not a burn. Next slide, please. And that's the problem that we do right now. We have an ongoing project of INPE that's half a research project and half an implementation project that tries to identify the burned area. I'm not going into all the details, but we have some heuristics that say, oh, it looks like it was burned. But even so, we have some regions that we cannot be sure of if it was burned or not. In this case, we ask for an expert. So there's a guy that is going to look at the images and check what's going on and see, okay, this looks like a burn scare, or this doesn't look like one. So that's basically what the idea of the project to do. Thank you. Next one, please. So we still need the specialist, and these specialists, they are very good, but that's a lot of polygons. One of these images may have 1,000 of polygons that say that we have to identify. Most of them are automatic, but there are some that the specialists must take care each by one by one. So the most we can get is a 95% of true positives, identification of burned areas. But we need to learn more. We need to understand better what's going on. And we noticed that it's very different between biomes. For example, for the Cerrado biome and for the Caatinga, the signatures of the scars are very different. Next slide, please. So one of the ideas that Olga is working right now is that we usually process each pass of each scene of a Landsat image separately. So when we look for the polygons, we only look on that image. We don't get any kind of training set. We don't have, sometimes we don't have information because they are very close to regions where they have a lot of clouds. So the idea is that let's not use only the Landsat image, the path that we are using. Let's take a look around. So the idea is that we are creating a database that classifies scarce polygons in one image based on that image and on the neighbors. Next one, please. That's the training, that's the main study area that we have. We have 8 images. You can see that's it's very small, but you can see points in blue and red that are corresponding to each one of these points is a small polygon corresponding to fire and not fire. That's scarce and not scarce. So we have 120,000 polygons. 75 of those, 75,000 of those are burned, and the others are not burned. Next one, please. And this is an explanation of the features that we're using. We are using right now 29 features. And strangely, these are not enough to separate. You can see, for example, on the band 2, 3, and 4 of the Landsat 8, we can see the difference from burned and not burned, burned in red and not burned in blue. Sometimes they are very close, so we cannot just use the bands, but we are using them anyway. Band 7 is exactly the same thing. Next slide, please. So we have all these vegetation indexes and some more. You can see that some of them, they have more or less a capability of separation. Yeah, they can separate between burned and not burned, but most of them are not really very, very helpful. Next one, please. So these are the experimental results. So we had we started to train with neighbor images and see what happens with other ones. All we devised 4 different schema for that. And she got interesting results. Interesting in the sense of, in most cases, if the image covers more or less the same biome or a similar biome, you can train with data of one image and classify, try to classify with other one. So we get, we still get the 95%, sometimes less, sometimes more, but the results are promising. Next one, please. So the idea seems to work, but we are noticing that using a single Landsat image as unit is very complex because it's a large image, even for Brazil. Sometimes you have different biomes, and we notice that not only the image, not only what's on the image, on the biome that we suspect is important, but also we have some people working with us trying to get information on soil models. For example, we noticed that the time that you have to recover for a burning on the Cerrado, it's very different depending on the kind of soil that you have. And we haven't used that information yet in our research. So the next steps are more or less try to investigate smaller amounts of the image, not only the whole scene, and try to get ancillary information on vegetation and soil models. Next one, please. I think that's the last one.
This is the last.
Okay, thanks. Thank you very much, Lucia, for help on that, because I'm still trying to share. And now I have I'm not the presenter, I'm the share again, and ask if anybody have any question on this presentation. One people, send me a question, even an easy one will do. Nope. Okay, see, if we don't have any questions, I'm going to ask the next presenter to start preparing for presentation. It's going to be Amita Murali Krishna. She's going to present total solar irradiance forecasting with Keras recurrent neural networks. So Amita, if you can share your screen, please let us know.
Yeah, sure. Can you see?
Yes.
Yes.
Can you hear me properly?
Yes.
Okay. Hello, everyone. I'm Amita Murali Krishna. I'm a PhD student of the Applied Computing course at the National Institute of Space Research, known by INPE. This work shows the preliminary results of a beginning part of my thesis. For it, I had the contribution of my 2 advisors, Rafael Santos and Luis Vieira, and also from my course colleague, Adriano Almeida. I divided this presentation into 6
topics. I'll start telling about what is TSI and the motivation behind of predicting it. Then show the main aim of this work. In sequence, tell about the larger proposal concerning the objective of my thesis project. Then mention very quickly about the neural networks I'm using. Show the main results of the experiments, and finally conclude with some suggestions of future works. Basically, solar irradiance is the amount of radiance received from Earth, from the sun, sorry, by square meter. And when we say the total solar irradiance, this can be defined as a total radiance received at the top of the Earth's atmosphere. I'm saying the top before we have also the irradiance measured in the soil, in the ground. So in this work, we are talking about the top atmosphere per second in an area of 1 square meter and from 1 astronomical unit of distance. This distance, the AU distance, we say, is a distance between the sun and the Earth. The TSE forecasting is very relevant to studies of the Earth atmosphere layers, among other that use TSI as an influencer, like climate models, for example. The other application of the TSI prediction is in its time series reconstructions, because we have a lot of failure periods of data. I'll show more in the sequence. Here we have an amount of all the TSI data collected from different missions till almost 2015. We clearly see a big calibration discrepancy between the instrument's signals, you can see here, and when some studies needs a bigger amount or bigger data period, it is not possible to use only one mission data because you don't have a long period of data with only one mission, using only one mission. And for that and also for data failure period, the reconstruction task is important. The figure also shows here below the relationships between this is the number of sunspots on the same period, and the relationship between the sunspot curve and the TSI curves. And because of this relationship, it was chosen to use solar images with records of sunspots as input of the prediction workflow. So the aim of this work is to offer a procedure that performs the TSE estimation, which can allow its reconstruction, but also predict its future variation 6 hours in advance ahead, using neural networks implemented in free programming languages and library. Sorry, language, only one language. So now I have here 2 types of sun images we use in this work. We use only these 2 types. Both are records of the sun photosphere. Essentially, we can call the photosphere as the solar surface. They are collected in different wavelengths, but show the sun in the same instant of time. The left one, it's a magnetogram, which shows in black and white regions what we call active regions. They are regions on the solar photosphere where the sun's magnetic field is very disturbed, explaining in a very healthy way. The right image is also required for the photosphere, but now in a visible light. If we could look at the sun directly, please don't do that. Don't try to do that. We will see something like this. And in this kind of image, we can see the sunspot, what we call the sunspots. If you take a look at both images, we can observe that the sunspots and their active regions occur on the same regions of the solar disk. That is why the sunspots appear only the sunspot appear only when the disturbance is very, very, very deeper. So we use those images as input for this workflow. The sequence of algorithms implemented for the workflow was based on, I didn't put here, but we have in the next slides, on the work from Vieira et al. I have a link, this information after. And it consists basically by downloading the sets of images for all the period we opted to proceed to process, identify the active regions and sunspots, classifying the identified regions, and calculating the areas of those distributed regions for each class of size and each class of solar disk ring. We have the solar disk divided by rings, and it's sorry, I summarized all the steps, but you can find a more detailed explanation in the article. With the areas calculated, they are used 40. Each input has 40 areas calculated to use as the input of the neural network, and then forecasting the TSI signal. As I said at the beginning, we have a larger proposal that was still partially considered till the end of this work, but is a proposal to offer with this workflow, turn the workflow accessible. It means available on free platform, language, and libraries in the cloud, so that it can be used by an interested researchers with the originally used versions, and then can be modified after. Reproducible with notebook code that can be re-executed to validate the developed procedures and then the obtained results, or edited to allow the reuse of the workflow. Also modular, to allow parts or modules of the workflow to be used separately, or edited to have part of the process replaced. I put this workflow again, so now you have the work which I use to as base for all the implemented algorithms. The intention is turn it available, the workflow available, and allow, for example, the process of a different database, so we can change this box to a different database, or use a different period of data, or to use the different techniques on the partial steps, like when we have to classify here the image, the identified regions, we can use a classifier, machine learning classifier maybe, or even change the prediction here, the technique is used to predict the TSI in this case. So originally we have a workflow written in MATLAB, and we changed this workflow to we translated it to Python and used in this case the keras. So we took an entire workflow in MATLAB. The original workflow used a recurrent neural network from the MATLAB Neural Networks toolbox. So we also opted to start the first test, the first experiments with the keras recurrent neural networks. And for that, we chose the keras library and the simple RNN, the LSTM, and the GRU to start the experiments. I think everybody at least have an idea about the recurrent networking, but basically they are used to sequence data where or time series. There can be where we can find a dependence between the input sequence. On the RNN, we have connections not only between layers, as we have in traditional neural networks, but also between units of the same layer. The RNN, the recurrent neurons or recurrent units process not only the signals are coming from the layer behind, but also its own output. Roughly, it is a way to implement the idea of memory. That what differentiates them for the other neural networks. In the experiments we did for each net architecture, we varied the hidden units, number of hidden units, with and without a dropout layer. We varied also the batch number and the dropout rates. We varied also the time step. And for all the occurrence measurement, we use the root mean square error to accurate the results. So first we have here the hidden units varying results. Here we have box plots comparing the performance between the test where a dropout layer is not used, and this is a dropout layer used with a 0.2 rate of dropout. For the test without dropout layer, we used a few units, hidden units, and for other batch of tests, we used more units. You can see here 10 to 80 units. We can observe an improvement in the results when using 50 units or more. Don't have much variation after 15 units. Then various time step, we have these two box plots. We can see this is not the same axis, the Y axis. In the left, we have the three architectures being compared, and we can clearly see that the LSTM and the GRU are superior to the simple RNN. So the second batch of tests, in the second one, we didn't use the simple RNN, and we're only comparing the LSTM and the GRU. Well, in these experiments, we can see better results with the 3 as the time steps, maybe suggesting something about the time dependence on the data input. This slide shows the graphics comparing the predicting performance for the 3 different actitudes. I think comparing those, we can discard the simple RNN, definitely discard the simple RNN. And between the two, the two with a better performance, we see a little better performance for the GRU net. Well, concluding, after all these preliminary results, we concluded that it's worth investigating better the possible time dependency in the input data. Once we are talking about the preliminary results, we intended to use a larger set of data, like a year of data. For this work, we used about 4 months of data. And the next step is predicting the spectral solar irradiance, not the total, the spectral solar, the SSI, is the irradiance in different wavelengths, and keep moving on to the larger proposal. I think that's it. Thank you.
Thank you, Anita. We are open for questions. If somebody have one question, because we are running a little bit late. I can't ask questions because I'm part of the work, so I'm going to ask a lot of questions to Anita later. So if we don't have any questions, I'm really sorry, we are running a bit late. I'd like to ask for the next presenter. That's going to be Mr. Okay, thank you very much, Anita. The next presenter is going to be Mr. Rodrigo Adeu. He's going to present assessing satellite image time series clustering using growing SOM. Rodrigo, can you share your screen and start the presentation as soon as you can? Thank you.
Okay, Rafael, thanks. I guess my screen shared. Can you see this?
No, we're just looking at your webcam. That on the bottom row, the first button on the left.
Oh, I click on it, but I try to share. It gives no message errors or says nothing.
Okay, Lucia, can you share? Can you help us on that?
Yes. If you want, I share the presentation. I have.
Can you do that? Thank you very much.
I think. I suppose. Just 1 second. Okay, is this?
Yes,
okay.
Thank you.
Okay, just 1 second that I turn off my microphone.
Okay, thanks,
Okay,
Lucia.
Rodrigo.
Thanks, Rafael. Hello, everyone. My name is Rodrigo, and I will present my work. It's called Assessing Satellite Image Time Series Clustering Using Growing SOM. It's a work developed at INPE, the National Institute of Research, Spatial Research in Brazil. And my work was made by me, by my supervisors, Karine and Pedro, and by my colleague, Lorena Alves. Can you go to the next slide, please, Lucia? Okay, this is a quick agenda. I will start with an introduction about the time series clustering using the regular SOMs. And after that, present you the growing SOM. It's an alternative to the traditional SOM. The customizations made on the growing SOM to fit the satellite image time series clustering. the results that we got with this work, and the final remarks. Oh, please, the next one. Okay, so here we have the motivation. When we have a lot of satellite image time series and we fixed a point in the space, we can measure a lot of data about this point and follow these measures over the time. On the next slide, please, Lucia. We have an example about vegetation indexes. So we fixed a point in time, look at this point over the time in several images retrieved from satellite satellite images, and then we are able to look at how this vegetation index changes over the time. On the next slide, please. In this work, we have used a data set from the Mato Grosso state from Brazil. It contains 2,000 samples from vegetation indexes from the Mato Grosso state, and we did exactly what I just said. We fixed some points and look at these points and try to understand how the vegetation indexes are changing over the time. On the next slide, please. We applied a computational algorithm called SOM. It's called it's a kind of algorithm that clusters data. So we changed the algorithm to present it instead of scalar numbers, we present time series. So it self-organizes it and cluster the data based on the input data. So the next slide has some examples extracted from Lorena Santos' work that shows how these samples were clustered into different classes. What we are doing here is present the data to a self-organizing map, let it run and organize this data and present us the clusters. And then we look at each neuron of this network, this neural network, and look at the samples that were associated to it. And then we label the neuron based on the samples, the classes of the samples that were most found on this neuron. But we have a characteristic of SOM that is the grid size. So before we start to run the algorithm, we need to specify the grid size of the SOM to run the data. And this is a problem because users of the data usually understand a lot about the data, but they are not specialists on neural networks. So it's a little bit difficult for them to predetermine the grid size. So the next slide, please. We are proposing an alternative to SOM that is called the growing SOM. This is an algorithm proposed a long time ago, but we are changing it to fit this data set and this approach to time series. So I will explain to you how this growing SOM works. It starts like a traditional SOM. The user needs to provide a spread factor that is a number between 0 and 1. And it's a neutral factor, so it's not related to the data itself. It's just how much the data, the network will grow. And it starts as an ordinary SOM with 2 plus 2. We present the sample, in this case is the time series. And there's a difference from the growing SOM to the regular SOM that we accumulate the error on each neuron. And then we look at this accumulated error on each neuron. And on the next slide, please. We have two conditions. If the neuron is a boundary neuron, so we need to grow the network. In this case, the neuron, we are using the neuron 4 to make an example. And if the accumulated error on this neuron grows above a threshold, we create 2 more neurons on the neighborhood. The other condition on the next slide, please, is when a neuron is not a boundary neuron. So in this case, the neuron 4 has already neighbors on all the directions. So we spread the error over these neurons to create conditions to spread the network on the future time. And this algorithm will run several times, growing the network based on the data that was inputted. The next one, please. So we did some customizations on the algorithm. The original GSOM algorithm has a learning rate that increases with the number of neurons, but we didn't got good accuracy of the whole network with this learning rate. So we changed it to a learning rate that decreases with the number of the iterations. This is the first modification. And the next one, we changed, the algorithm says that we need to provide a neighborhood influence, but it does not specify this function. So we tested a lot of functions, and then we use this one that's decreasing with the number of iterations, and then decreasing with the distance between the winning neuron and the neighborhood size. The next one, please. So here we have some characteristic of the data set. It's composed by 9 classes. We run for 15 epochs, 10 for growing and 5 for smoothing. And each time series has 4 attributes of vegetation index concatenated. So I will present you the results of this work. The next one, please. First of all, the network topology. On the right side, you can check that the GSOM algorithm really grows with the data presented to it. It's not squared as the traditional GSOM that is on the left side. And the number of neurons in each class, it's almost the same one. But we were able to check the network topology growing as the data was presented. On the next slide, please. We can compare the performance of the SOM against the GSOM. And we can see that on the initial interactions, the GSOM runs on a small time comparing to SOM because it does not have the whole network. So the algorithm runs faster on the beginning. But after we have the setup of the network, the running time, it's almost the same. On the next one, please. This is the cluster accuracy for 15 interactions of SOM and 15 interactions of GSOM. And we can check that the GSOM is a little bit better, 2 percentage points better than the traditional SOM with the same number of iterations. And on the next slide, we have the comparison between 100 SOM interactions that was used on Lorena Alves' work and 15 iterations of SOM in this work, and they got almost the same accuracy for the whole network. There are small differences between the classes, but the overall accuracy of the map was almost the same. On the next one, please. We look at the neighborhood, and this is another execution of this SOM, and we compare the farther neighbors with the closer ones. So here we extract the neuron 1 and compare their weights with the nearest neurons and the farther neurons. And on the next slide, we can see that the nearest neurons are closer. They have closer weights than the farther neurons. So the distant ones have a lot of error inputted into it, and the weights of these neurons are not close to the nearest neighbors of the reference neuron. On the next slide, please. We have the numbers of this comparison. So to assure that the neighborhood is a relevant number and it kept on the GSOM as it was kept on the SOM. On the next one, please. These are the final remarks. So we check that the GSOM is applicable for the time series approach. It's a suitable SOM alternative with good performance, good cluster accuracy, and keeping the closest neighborhood intact. We develop a Python package, and it's available on GitHub. And the most important, we avoid the previous grid side parameter. We just use the spread factor that is a neutral factor. so we don't need to say the size of the grid before we run the simulations. I guess this is the last one. Oh, thank you so much for everyone, and if you have any questions.
Thank you very much, Rodrigo. We are open for questions. That's the last presentation on this session. If anyone has a question, you can type it on the chat, or you can turn your microphone on and ask. And if nobody has questions, I have to have one. Rodrigo, just out of curiosity, when you have a large sum, a traditional sum, you end up sometimes with dead neurons that doesn't correspond to anything. They are just that they are using space. Did you get any time that you run the growing sum to get a dead neuron?
Yes, Rafael. If we use a spread factor very near to the number 1, that is the max one, sometimes we have some dead neurons on the network. But it's connected to the amount of growing epochs. If we use a spread factor near to 1, but we use a small amount of growing interactions, we don't see the dead neurons.
Okay. Thank you very much. Any other questions? So if we don't have any other questions, I'd like to thank you, everybody, for helping, especially Lucia for helping us with the technical issue that we suffered with Jitsi. Thank you again, and I hope everybody enjoy ICCSA. The program is already online, it's fully online. You can see all the presentations. That's a lot we can learn with other presenters, and that's some very interesting keynote speakers. So thank you very much, and good day for the people in Brazil. Good night for the people in Europe. Thank you.
Thank you so much.
Thank you.
Thank you, Lucia.
Thank you. Bye.
Bye.